Right now, I plan to do a derivation of Gauss's law using the divergence theorem. So in chapter 16.9 for Math 1D, you've learned about the statement of the divergence theorem, which gives you another way to compute flux. So what the divergence theorem says is, when you have flux over a surface, you don't have to compute it over the surface. There's another way to compute it. You can compute the divergences of the field, vector field F, over in the entire volume instead. So if I were to have a surface, and let's say I had a field flowing through it, instead of having to compute the divergences, the flux through all the little areas on the plane ds, instead, the large arrows flowing in are your field F, and this is a volume. Instead of having to compute the dot product of ds with all these little field vectors and factor in the angle theta in between them, you can just sum up the volumes of the divergences over that entire region instead. So, this theorem, what it does is, it can only be used in certain situations. Notice the closed loop integral sign. When you use the divergence theorem, it can only be for a closed surface. You can compute the flux through an open surface, any surface you want, such as this rectangle. But if you want to compute the flux using the divergence theorem, this has to be a closed volume. So in this case, if let's say you had a rectangle or a sheet, you can't use the divergence theorem. But for a sphere, you can. And this theorem is pretty important. So, when you compute it, it only applies, you only have to worry about the divergences within your volume. The word within is really important here. So what happens is, if let's say I had a divergence of the math field outside the sphere, let's see right here, it would not affect the flux. It would not affect the flux through the surface. Only the divergence of the field enclosed within this sphere is going to affect the value of this flux integral. But before I do the derivation for Gauss's law, I have to talk about the divergence operator first. So, when you talk about divergence, we use this operator del, which is the gradient. But instead of taking the gradient of something, let's say of a function, x, y, z, we dot it with a vector function. And what this divergence operator does is, you're dotting it with a vector, and your final answer is a scalar number. Now, intuitively, the divergence operator measures how much something flows out or flows in out of a certain region. So in this case, I'm going to use electrical charges as an example. Let's say you have a positive charge here. If this was a region in space, if the plus charge was a region in space, the divergence of that region in space, indicated by the black circle, would be positive. So del of your electric field here, x, y, z, it would return a number greater than 0. It would return a number greater than 0. Now, the field is actually in 3 dimensions, but in this case I'm just drawing 2 dimensions for simplicity. Now, if you had a negative charge instead, you have the field lines flowing in. Quick note, in the case of the positive charge, notice how the field is flowing out of a region of space. The net flow outward is positive. Now, in the case of the negative charge, when you take the divergence of this electrical field, it doesn't have to be an electrical field. It could be any mathematical field. But when you take the divergence of this blue field, it's a number less than 0. Now, what this means is that the net flow is negative, and so it flows inward. There's a net flow into that region of space. When you have a net flow inward, there's another term for this. We call this a sink. So you can think of this as the kitchen sink in your bathtub. The water is flowing, all the water is flowing into that region in space. And for this positive charge, you can think of this, when the divergence is positive, as it's a source. There's a net flow outward flowing from that area. Now, what happens in the case that the divergence is 0? In the case that the divergence is 0, let's say my vector field is uniform. In this region of space right here, notice the flow in is equal to the flow out. Thus, when you take the divergence of this mathematical field, it equals to 0. Net flow in equals to net flow out. But what's the actual number that you get when you take the divergence of the electrical field? When you actually take the divergence, something really interesting happens. What happens is, when you take the divergence of E, you get a number of rho over epsilon naught. Epsilon naught is just a constant, so think of it as almost correcting the units in this case. But what it does is, the divergence of the electrical field is proportional to the charge density rho for that charge or for that volume in space. In other words, if you have a very large divergence or very large flow from an area out, so this is a source, that means there's a very large positive charge density there. If let's say you had 2 positive charges, one is just a single positive charge, or for that volume, very small positive charge density. And in this case, you have a lot of positive charges over this volume. when you take the divergence of this, notice how the arrows are longer. The divergence of this case is actually going to be larger than the divergence of this case. And notice, by this equation, this must have a larger charge density. Because the amount of flow is larger in this case compared to this case, that means this rho must be larger for this than for this. So in this case, this rho, this plus rho in case B is much larger than the positive charge density for case A. And same thing for the divergence. The divergence of E of B returns a much larger positive number than the divergence for case A. Now, for negative charges, if you were to draw this out, the same situation occurs. In this case, you only have one negative charge, or a very small charge density. But in this case, you have a very large negative charge density. That means when you take the divergence of this, the divergence of, in this case, let's call it point C, it returns, let's say, a small negative number. But for this case, the divergence, I'm running out of space here. In this case, the divergence for the case D returns a large negative number. And using this equation, what happens is, this is a small negative charge density. So for C, you have a small negative charge density. But for case D, you have a very large negative charge density. Now, to prove Gauss's law, I have to convert this form to the integral form that we've been using so far. So let's return to this. Recall that for Gauss's law, your Gaussian surface has to enclose the charge. It can't be an open surface like this. It must fully enclose the surface, either in this shape of a Gaussian sphere, a Gaussian cylinder, or a Gaussian pillbox, or perhaps a Gaussian cube. Now, to do the derivation, let's start off with the electric flux that we're trying to compute. Now, when you actually do the flux integral, it's actually a double integral over the volume. In textbooks, we can represent Gauss's law as a single integral closed loop E dot dA. But just remember that mathematically, to actually add up all these little shingles in both directions, you actually need to do a double integral over that surface. So you would need to integrate in terms of a parameterized value in both u and v. Now, for computing the flux, when you actually compute it, what happens is, when we either write ds or dA as a vector quantity, it's actually equal to the normal vector times that area element. And that area element is actually in terms of dx dy or in terms of du dv. So this is your flux. And then by the divergence theorem, is equal to the volume integral of the divergence of the electrical field over this volume. But when you take the divergence of the electrical field, recall that this equation in differential form describes the behavior of the electrical field. That means we can simplify this whole expression to integrating the charge density rho over the volume. But when you're integrating density over a volume, your final answer, let's pull the constant out first. When you integrate charge density over a volume, what you get is the Q net, or the net charge enclosed by that Gaussian surface. So in this case, when we're doing this step, let's pretend this is our Gaussian surface. Let's say we have a bunch of positive charge in here. This is one, this is one, this is one, and they're all distributed within the volume. When you're summing up the rho of the D volume, you're adding up all of these little charges within that volume of space. That's why we need a triple integral. And that's actually it for the derivation of Gauss's law. Notice how you've gone from the flux integral all the way to Q net. Sorry for the camera. Notice how you've gone all the way from the flux integral to the charge enclosed. By using the divergence theorem, these two quantities are identical. But right now it still feels a little vague, so I'm going to do a few examples later.